Applications of exponential functions, financial formulas and problems, part 2, present and future value. Future value. For the compound interest equations, it is assumed that the investor makes one lump sum payment at the beginning, and all growth in the account is interest. This approach is true for share and certificate of deposit accounts, but many accounts allow the investor to continually add money over time. For an annuity, an investor makes a sequence of equal periodic payments. In the case of an ordinary annuity, deposits are made at the end of each period at the same time that interest is posted in the account. The total value of the investment return from an annuity consists of all the periodic payments together with all the interest. This value is called the future value of the annuity because it is typically calculated when an account advisor is projecting into the future. For an account paying an annual rate of R%, if compounded interest and deposits of R dollars are posted N times per year, the future value of the account in T years is given by the formula future value equals the payments times the quantity 1 plus R over N to the NT minus 1, all divided by R over N. This is a rather messy formula. Since R over N% is applied to the annuity during each period, we can simplify the formula by letting I equal R over N. The simplified formula is future value equals the payment times the quantity 1 plus I to the NT minus 1 over I. Let's consider two examples. Meredith has a retirement savings account into which she makes bi-weekly payments of $400. The account pays an annual interest rate of 6.5% compounded bi-weekly. Meredith plans to make deposits for 40 years. What is the future value of the account? We begin by listing what we know. We know that the 6.5% rate becomes 0.065 as our R value. Since it's paid bi-weekly, 52 weeks in a year divided by 2 means 26 payments. Each payment will be $400, and the term of this is 40 years. Let's find our I value. Taking 0.065 and dividing by 26, we get 0.0025. Plugging into the future value equation, we now have 400 times the quantity 1 plus 0.0025 raised to the 26 times 40 minus 1 over the 0.0025. We can simplify that so that now it's 1.0025 to the 1040 minus 1 over 0.0025. Completing the computation, we obtained that the future value of this account is approximately $1,987,219.92. This is using 6.5% interest compounded bi-weekly on $400 payments for 40 years. Tim wishes to retire in 30 years with $2 million. If his retirement account pays 3.24% interest compounded monthly, what must Tim deposit each month to achieve his desired future value? Again, we list what we know. We know that our rate of 3.24% gives us an R value of 0.0324. Since we're compounding monthly, our N value will be 12. We don't know the payment amount, that's what we're looking for, but we do know that the desired future value is $2 million and that the term will be 30 years. Finding our I value, we find that I is 0.0027. Plugging into the future value equation, we have 2 million equaling our payment times the quantity 1 plus 0.0027 raised to the 12 times 30 minus 1 over 0.0027. Simplifying, we're going to obtain 1.027 raised to the 360 minus 1 over 0.0027. That becomes 607.3206237. Dividing 2 million by that, we find out that Tim's payment must be $3,293.15 every month for 30 years. Present value. At any time during the year, the average American has less than $1,000 in his savings or checking account. For this reason, purchasing a house, buying a car, or paying college tuition requires a loan. The value of a loan at origination, i.e. the amount borrowed, is the present value. The present value, along with annual interest rate and the term of the loan and the number of annual payments, is used to determine the amount of each loan payment. To keep the math fair and simple, the number of payments is usually equal to the number of times per year that the interest on the loan compounds. If a person takes out a loan at a rate of R% compounded n times per year, the lender will expect the borrower to make n payments per year of R dollars for t years. The present value of the loan at origination is given by present value equals the payment times the quantity 1 minus 1 plus R over n raised to the negative nt divided by R over n. Again, this is a fairly messy formula, but we do have the R over n. Since R over n is applied to the remaining loan amount during each payment period, we can simplify the formula by letting I equal R over n, just as we did for future value. This gives us a simplified formula of present value equals the payment times the quantity 1 minus the quantity 1 plus I to the negative nt over I. Again, let's consider two examples. Michael takes out a loan to purchase a house in Roswell, New Mexico. He agrees to pay $706 per month for 30 years at an annual interest rate of 5.75%. What was the value of the loan at origination, in other words, the present value, to the nearest thousand? Listing what we know, the rate of 5.75% gives us an R value of 0.0575. Since we're making this monthly, our n value is 12. Our monthly payment is $706, and the term will be 30 years. Finding our I, 0.0575 divided by 12, is approximately 0.004792. Plugging into the present value formula, we find that our present value will be $120,973.63. Rounding to the nearest thousand, that is $121,000 as the present value for our loan at origination. Michael's friend Max needs to take out a loan of $150,000. If Max makes quarterly payments for 15 years at a fixed annual rate of 6%, what is Max's quarterly payment amount? Again, we list what we know. A 6% rate gives us an R value of 0.06. Quarterly means that the n value will be 4. We don't know the payment, that's what we're looking for, but we do know that the present value at origination will be $150,000. And we know that the term will be 15 years. Again, we find an I to make our computation easier. In this case, our I is 0.015. Plugging into our present value formula, simplifying and dividing, we find that the payment should be approximately $3,809.01. This concludes our video on present value and future value.